I am Brian Sam-Bodden. I work for Redis as a developer advocate. I've been doing Java since 1997 or so. And now we have mics. And today, I want to talk to you about vector similarity search. In VSS, or vector similarity search, in Java, it's a pretty unexplored field. Mostly because the machine learning AI world and the Java world have very little overlap. If you do any Python, you've seen that the Python community has been moving super fast with all the AI stuff. And that's what made Python kind of pass us in the last few years as the most popular language. And one of my goals in the next few years is to try to reverse that. And I'm talking about VSS in Java in Spring with Redis. Let me make this a little bigger here. All right. So I'm bsb@redis.com. You can find me on Twitter at bsbodden, and that's my GitHub handle. That's me before the pandemic, when I thought it was going to be like maybe 4 weeks of being at home. So I started drinking beer heavily. And well, this is what happens. Moderation. All right, so vector similarity search. Let me give you the too long I didn't read. So why? A lot of the, whoa, now I'm loud. A lot of the data that we get now, it's unstructured data. We used to be able to have small amounts of data where we could basically manually curate it. We could extract features, turn a list of possible values into sometimes bitmaps or booleans or something like that. If you worked in, for example, marketing, you remember seeing databases where there would be like 10 fields, and then by the end of a 5-year cycle, they would have like 80 columns. And every column had some identifier about something that needed to be tracked in the industry in order to target advertisement and things like that. So this explosion on structured data has led us to not be able to react rapidly to the amount of data that we're getting and the complexity of the data. So a new breed of databases has spawned, and they're called vector databases. And the idea is that you will turn unstructured data into some kind of magic array of floats that then can be used to find other pieces of data that are similar to that data by different means. It could be different features of the data. One of the scary things about AI, of course, is that sometimes you don't know what those features are. If you've ever done a machine learning model where you find similarity between things, sometimes you find that the model finds similarities that humans would not catch. So for example, if you do facial recognition systems, you'll find out that there's little subtle things that the computers pick up now that as a human, you're like, well, I don't quite see it, but it's there. They have surpassed us now. Computers are better at object detection, facial recognition, you guys probably been hearing about the large language models. So that's a little scary, but also, helpful. So how many of you are using Redis at work? All right, so we can probably skip a little bit of the Redis intro. This talk, it's about searching unstructured data using Redis in Spring. So it's a big sandwich with a lot of layers. So we'll deconstruct it for everybody. So Redis provides vector storage now. So if you know Redis is a key value database. And the thing about Redis is that that's what most people know. They don't know much more past that because Redis is fast as hell. And being so fast, the first thing that Redis was used for was caching. And once something works well, caching, it's what I call a cross-cutting concern. When caching works well, nobody knows it's there. When it breaks, you're like, where's the Redis expert? We need some help right now. So being a system that kind of fades into the background has been detrimental for Redis as a database because it has a lot of other capabilities that people do not discover because Redis hasn't broken for them to go and learn more about Redis. So Redis actually has vector storage and search capabilities, which is what I'm going to focus the talk on tonight. So quickly with Redis, I'm going to talk about it. In case you don't know this, Redis stands for Remote Dictionary Server. In the dictionary part, again, it's the name value pair thing. The difference between Redis and most key value systems, it's that the value in Redis could be pretty much anything. From a JSON document to a probabilistic data structure, to a hash, to a set, a list. We even managed to jam a whole graph into a Redis key. Whether that's a good idea or not, that's a story for another day. But Redis also, another misconception is that Redis is an in-memory only database. So the moment you pull the plug, everything goes away and you lost your data. That's not the case. It is optionally persistent. So for some things, you might want to have Redis just to be in memory because you're using it as a cache. And if the cache goes away, you rehydrate it and you're good to go. But in some cases, you want to have that data be persistent and distributed. And in that case, you can basically flip a switch in Redis and have a distributed stored of data. So there's open source Redis, which everybody knows and loves. And on their open source Redis, we have a bunch of data types. The most common one is the string. Everybody basically, the string data type, it's abused in Redis. Like people will say, oh, here's like 5 gigs of XML, put it in a string. The problem, of course, is that you're gonna get it out and it's like, well, now I'm gonna have to parse it, I'm gonna have to do all those things. And the reason Redis has multiple data types is so you can pick the right data type for the problem at hand. So we have strings, we have sets, we have lists, we have hashes. Hashes is the workhorse of Redis because a hash maps fairly well to an object. And for the longest time, it's been the #1 data structure that it's used to map to an OO environment like Java. We have bitmaps, sorted sets. Sorted sets are very useful if you're doing anything where you really need to basically rank things. And sorted sets are also heavily used in like gaming industry to do like leaderboards and kind of gaming applications are very popular users of sorted sets. We have geospatial, so you can basically have long lat, not lat long. For some reason they have it reversed. I say lat long my whole life. I came to work for Redis and it's reversed. And you only find it when you break something where the two numbers are, one of them is out of range. I've been complaining about that, nobody hears me. So in bit fields. We also have streams. So you have the ability to basically have a Kafka-like stream where you can basically dump events and listen to those events in some other place. It's used a lot for synchronizing processes. You can use it as a work queue. There's a lot of different possibilities with the streams. So it's not quite a Kafka environment, but it's a Kafka-light. But it is fast. That is the trademark of Redis across the board is that everything has to be super, super fast. So I call those the foundational data structures. Then we have Redis Stack, which is a packaging of open source Redis with some extra things that we've built at Redis. And with Redis Stack, we have JSON. So now we have a data structure that's slightly better to map to objects than hashes. So hashes are good, and they're good for a one-level object. Once your object graph gets complex, then you kind of have to jam things into those primary level hash fields. So with JSON, obviously we can create more tree-like structures that can hold the data or objects better. In the translation, it's obviously faster to do something like OO mapping. We also have probabilistic data structures, which allow you to basically keep counts of very large things or determine whether something is there or not in a linear amount of space in a linear amount of time. So for example, let's say that you have a system that you have 1 billion users, you're a brand new unicorn, and your sign-up form has to determine whether the email has been taken by an account already. So rather than querying 1 billion row database, you can ask this data structure, is this email in the system? And in linear space storage, and in linear time, it will say, very likely. So they're probabilistic because there could be a margin of error, but it's very small, you can fine-tune it. So probabilistic data structure will allow you to basically do things like that and save processing time and storage time. So that's the second layer, documents in probabilistic. And then the third layer, it's search. And to me, search, it's what makes NoSQL databases really, really catch up to SQL databases. So in my mind, NoSQL plus search almost equals SQL. And we all know the advantages of NoSQL when it comes to distribution. If you guys remember in the old days, sharding a MySQL database, that's the point where you say, well, I need to find a different job now. So the search module really adds a lot of power to the data that you have in Redis. And also think about Redis, it's used for caching because it's fast. You can keep things in memory. And sending that data somewhere else to be processed, it's very expensive because it's typically a lot of data. So having a search module in Redis means that you can locally deal with that data. Find the things that you want and only send the things that you need. Similar to what we used to do with store procedures to save ourselves round trips on the network, but now it's emphasized because of the size of the data in the distribution of our applications. And we also have functions which allow you to basically do store procedures in Python or JavaScript, so you can basically write kind of your own Redis lambdas and send that code to execute on Redis against the data structures that you have stored in there. All right, so at the top level, there's Redis Insight, which is what I'm going to use today to do some of the demos. Allows you to basically, it's a GUI for Redis. Allows you to look at the data structures in search and visualize some things. And then there's my baby, Redis OM, which is the library that I started extending Spring Data Redis. So if you use Spring Data Redis, you know that Spring Data Redis provides hash mapping of entities and also secondary indexes. So Redis OM takes that and extends it by using the search engine and give you the ability to map to hashes in JSON and to do complex searches, like complex SQL-like searches and aggregations. And there's a bunch of other stuff there that I've thrown in there when nobody's looking, so I will show you some of that. Redis OM works with Redis, which is one of the two primary Redis clients for Java. And we also have Node-Redis and Redis Pi for the Python community. So those are our officially supported clients right now. And I'm going to stop doing air quotes, I promise. So this basically makes Redis what I call a real-time data platform. So I'm going to skip the tour of Redis because that's actually something that you probably have an idea of what it is. So let's talk about this whole data balance thing. And the data balance is, again, structured versus unstructured. We talked a little bit about this, but I'll give you some numbers. 80% of the data generated by organizations nowadays, it's unstructured. So that means you either are going to have to hire an army or basically put ChatGPT to work, basically turning that data into something that you can do actionable things with. In that percentage, it's only expected to grow. So this is kind of like the breakdown that they have in the industry of how the data is classified. So you have structured, anything that you can put in rows and columns in a database. Semi-structured could be like a spreadsheet or JSON, where you might have an extra document attached to another document, so you never have a specific structure set in stone. Quasi-structured, then you have things like data coming from a click stream. And then unstructured, images, documents, free-form text. Surveys where the user can basically, go to town and write like, this is why I hate your product because, and they'll tell you a story of their childhood and all their trauma, and then they say, and that's why I don't like your socks. And you're like, whoa, okay. All right, so how do we deal with unstructured data? Some of the common approaches are labeling and tagging. So I guess taxonomies and folksonomies. So either this belongs to this category, or let's put a tag on it, and there might be other tags coming down the line. And these things are very labor intensive. There are AI-driven systems now that do labeling and tagging. So they use basically vision models, language models, OCR detection to figure out, for example, in a picture, what is it that I'm looking at? There's a scene detection or scene descriptions. So AI obviously has, it's at the forefront of automating things like this. But they're still labor intensive, subjective, and error prone. So that's where the word embeddings basically pops up. And how many of you are familiar with embeddings? All right, some AI ML nerds, awesome. So I've been doing a master's degree in machine learning and AI, just because why not? It was in my bucket list. And I really got engrossed into this world. And pretty much what you realize now that it's a marketplace of AI models out there. And if you find the right model to match your data, you can create embeddings for that data. So that's the short story. Obviously, we've seen that machine learning and AI has leaped forward in the last decade or so. In the NLP world, there was a paper called Attention is Everything or something like that, and that's kind of like the turning point where all these large language models like ChatGPT basically started, people started going like, oh wow, this is really something. Before that, all the seed money in venture capital was going to vision model companies. And now the vision model companies are like, can we have some money? Because the NLP folks are getting all the money now. So computer vision in large language models or out of the NLP field are super hot industries right now. And they really have basically skyrocketed to the point that if you use ChatGPT, you're like, we need a better Turing test now for these things. Because they'll probably, they're able to pass most of the tests that we used to have for determining whether something is a human. So pretty sure, pretty soon, you will have basically ChatGPT help you do the I'm not a robot checkbox, and it's gonna be a self-fulfilling cycle. All right, so, oh yeah, this is for Josh. He's not here, but don't tell him. So remember I told you that before you basically had to extract things manually, even when we had already machine learning models. For example, if you have some piece of raw data, like a shirt description in here, a product, where you had a price and a category, you still had to basically do things to satisfy how the machine learning models can consume that data. So one way is to basically do what we call one-hot encoding, which basically means create a bit mask of all the categories, and then for the categories or the taxonomies, or the folksonomies, the tags that match your product, then you flip that bit to 1. And so we still had to do that for a lot of data. And also, we have to figure out what that data should be. So in this case, it's a very simple concept, or category. But what about the fabric? And what about the pattern in the fabric? And what about the colors in the patterns in the fabric? What about the color type? What about whether it has a button high or low? All those things, can you imagine breaking that data that way? And that's where the modern AI models come into play, because they detect what I call latent features. So not what I call, what everybody calls. And the idea is that there's features in there that you don't even know you're trying to get out. For example, I'm gonna show you a demo on facial recognition, and I kind of gamed the demo a little bit, so the examples that I give it will return what I wanted. And for that, I had to do certain things, like for example, the orientation of the person's face in a specific. So if there were two people that look almost the same, and you give them a picture of one that it's not, if that person was, their head was tilted or their teeth were showing, it might match the wrong person just because the original picture you're trying to match against were showing teeth or something like that. So there's a lot of things in there in machine learning that it's hidden under the covers. For example, ChatGPT being a chat interface bolted on top of a GPT-4 model means that there is layers and layers and layers of basically controllers and state machines to basically prevent bad things from happening and also guide the underlying model to do things. So it's not all completely AI. There's a lot of programming there that it's basically hand coding rules. The traditional old school AI rule engines, decision trees, all those things are still there at that level to then curate the stuff that comes out of the machine learning models. And here's a typical example of just from the world classification. Is this a shirt or a jacket? And there's a gray area. As you move to the right in here, you can see that there's a jacket-ish shirt or a shirt-ish jacket. And those are problems that we had to basically deal with by hand before. Now with AI models, some of those things can be extracted automatically to basically enrich our data. So that brings us to automated feature engineering. So again, ML models can extract latent features, which are the features that we don't even know that they're there. We also can grab the gray areas of something. Remember, the one-hot encoding was either yes or no. But with AI models, you have a range, typically between 0 and 1. It's like, how-ish is this thing applied to this specific entity? So the process of generating the embeddings, we call it vectorizing, or at least it's more of a programmer term. Like the machine learning folks will basically say, embedding generation. Programming nerds like me will say vectorizing, because that's the end result. So vectorizing is generating vectors and embeddings from the data. And the process is to basically choose an embedding method, clean and pre-process the data as needed, and train the embedding model, and then generate the embeddings. So again, the semantics, the meaning of the data. So for example, if you were to go to an example of a scene, there's a person picking flowers in a park, and there's a pond with ducks. Grabbing the semantic of something like that, it's complicated. And that's where language models and vision models basically kind of merge together. And you can really get a scene description, but also figure out what is the most important thing in that scene. So maybe the dogs, break dancing in the background, even though it's very odd and strange, it's not the most important thing for this specific scene. I don't know why I thought about break dancing dogs, but So there's two options here. Use a pre-trained model. That's the easy option, and the one that in, I would say, 80% of the cases, it's what you want. Or train your own models or enhance the training of a pre-trained model. So for example, you could find a vision model like YOLO, or YOLO 5 or 7 or whatever it is that they're to this day, and then say, here are all the products from my company, let's actually add them to the training set in the testing set of that specific model. So then at the end of the day, once you have these embeddings, then vector similarity, it's really a downline tool to search for things that are similar in that vector space. So let me now show you a little bit of a demo here before we move on so you can get an idea of this. So this is a Jupyter notebook, but it's a Jupyter notebook running Java because I refuse to show you Python code. That would be cruel. So one example that I have in here, and let me make that a little bigger, unless you guys have laser vision. Let me see if I can, okay. Is that big enough? I'm only gonna ask once. Yes. All right. So let me, I think I've ran this too. So if you're not familiar with a Jupyter notebook, it's basically an HTML base environment where each cell can have code, and then you can see the results of that in there. Typically, they're Python or R, but you can actually jerry-rig them to basically work with Java. So I'm using something called DJL, which is a AI ML framework for Java. And you can see here that there's some Maven directives in here. This is basically my embedded POM. Down here I have some imports. And down here I have a model. And this is a very simple model called Glove, which is a extension of Word2Vec, which basically means how do I turn words into vectors so I can put the vectors in a vector database and search over them. So in this one, you can see that I've run these 4 words. These are the traditional words to basically showcase vector and vector similarity. So king, queen, man, and woman. And up here, I created a model that basically, given a string, will give you something called an ND list, which is basically an array of arrays. And here's the location of the model, and I want the embeddings to be 50 floats long. So I want an array of 50 floats out of my words. So I have my 4 words in here. Notice that once I run this, I call embedding embed text, passing those words, and then I can get them out by index. So once I do that, notice that here I printed the shape of the king embedding, which is 50, and same with the queen, 50. And these are the numbers that come out of the embedding. So that's the representation of the word king given that Glove NLP word model. So once you have those, then you can do some fun things with them. So how many of you have written AWT Java code recently? This was a trip back in time. So I have to create a buffer image. So basically, I ended up writing AWT code because we don't have all the same libraries that they have in Python to do cool visualizations. So you can probably ignore this, but so what that piece of code is doing, it's colorizing each one of those 50 values between red and blue. And this is not an original idea. Somebody in the Python world did this for a tutorial, and I really liked it. So that's what I did, but in Java. So in here, you can see that the word king, it's represented by that rainbow, and queen, man, and woman. So that's pretty cool. You can see that there's some similarities in here. I like to think that this red band in the middle here represents that these are all humans. But obviously, it's probably not. They all have a little bit of something that you don't know what it is. And remember, in this vector space of words created by this model, that model was trained with Wikipedia and other things. So all the biases, all the sexism, racism, everything that is wrong with a large group of texts will probably be reflected in those vectors. So that's one of the reasons that there's a whole movement for ethical AI where you basically try to correct those things within reason. So in here, the typical example that it's used, it's that king minus man plus woman should turn into queen, or should be close enough to where queen lies in that vector space. So that's kind of how similarity works, because you can do additive operations, you basically do vector arithmetic to basically say, well, what if I have, that shirt and those pants, and kind of create a mishmash of things to find something that might actually match in terms of colors or fabric. Of course, you're never not gonna know which features are gonna be matched, but it's kind of the idea behind this. So here's what king minus man plus woman is, which should be, I called it queen-ish. And that results in an embedding too, because those vectors can be added and subtracted. Then right below, I did some distance. So one of them, it's a cosine similarity. So you basically take 2 of those vectors and you calculate the cosine between them. And if the angle between them is close to 0, they're pretty similar. There's also Euclidean distance to basically, so here's the vector 1 and here's the vector 2, and that, how far apart are they? And I'm gonna show you some graphics that will basically make this a little more clear. But at the end of this, I printed a table, and even though it's not exact, when you visualize them in a vector space by doing like principal component decomposition and things like that, they're kind of close. But again, all the, I've seen other examples where the biases in the text actually surface. Where, for example, you would say like a person plus white coat, it's plus man and then equals doctor, and then plus woman equals nurse. And you're like, really? So there's stuff like that. I mean, obviously that's where the interfaces to systems like ChatGPT, that layer of code that has to be between you and the model, has to deal with those things. All right, so let me show you, and here's another one of distances. So you can see that the distance from king to king is always 0, obviously, and then here is king, queen, and basically the whole matrix. So let me go back to the slides here. So again, where do you find these models? There's a lot of places to find these models. There is Hugging Face, which, you know, there's tons of different models in there. OpenAI has a lot of models in there that you can use. They also have their own hub now. PyTorch hub, TensorFlow, all those frameworks that you hear about in the machine learning world, they all have pre-trained models in what we call model zoos. So you can, with the right Java framework, you can plug in into those models and get that, them to basically do work for you. Make this a little bigger. Okay, one example is I use something called SentenceBird, which is rather than just tokenizing or vectorizing a word, you can vectorize a sentence. And that is actually much more useful because it really extracts the semantics of the sentence rather than just the word with the average usage. So as you can see, there's tons of models. In this list, you can see at the top has performance metrics. And this list keeps on getting topped. Like sometimes every couple months, there's a new model that's better than the prior one. So this industry is just moving at a breakneck pace. It's almost scary. So now let's talk about vision. So when you want to vectorize something that is an image, so there's a lot of image classification models where you have millions of images and then you have a certain number of classes that they can land, you know, typical cat, dog, hot dog, food, all those words can be classes at the tail end of those models. And we don't really want the classes when we want to create vectors. We want to basically tap into those models somewhere in the middle and grab something that is flat that we can use as a vector. So as you can see to the right of that, this is a typical vision model. So it'll do convolutions at the beginning and basically scan the picture to grab features out of it and slowly flatten. And then typically you get some layers at the bottom that are the pooling layers. And in there, you can basically grab some of those vectors and use them as embeddings. All right, so let me actually go and create some other vectors for you. With a Java application, not in, make this big. All right. So I have a little project in here where I have a picture from yesterday. This is from the Sean's session. And in that session, I took a, just the obligatory selfie of the, well, that's not a selfie, a picture of the audience. All right, and in here, and this is gonna be the foundational code for the demo that I did later. So in this retina face detection, the Java, is that big enough? That's good, okay. So in here, at the top, you can see that I'm basically running something called retina face detection, and I'm saying predict. At some point, I'm giving it a file. So this was the largest selfie. Let me switch to the image that we have in here, which is audience 1. And it's a PNG. I refuse to say ping. I don't like that. So audience 1 PNG. All right, so we have our audience 1 PNG plugged in there. This specific model, I use 2 models. One, to basically do facial detection, which basically means find all the faces in the picture and create a bounding box around them. And then I use another one that allows you to extract that specific, the most prevalent face in the picture. And you can see here that I'm using a model from the PyTorch model zoo, which is called retina face. And so that's the funny thing. I'm using PyTorch, which the Py part should give you a hint that it's from the Python world, but I'm using it in a Java application. So this DJL framework allows you to pipe into about 6 different frameworks that are Python and Java. So you can basically use all the models that are published in there, or whatever models they can get to, then you can get to them through DJL. So I'm pretty excited about this project. So you can see here that I actually using a criteria to find the right model, and then once I find the right model, if I couldn't find a model with this specific characteristics, that build command there will fail, and I would have to start playing with parameters. And once I do that, I'm basically saving the bounding box image, and then I'm going to grab the most relevant face out of the equation there. So let me show you that here. So let's do I'm gonna run the retina face detection, and let's see, this should end up in the output folder down here. Do you guys know the theme to Jeopardy? So the more faces that are in the picture, the longer it will take, obviously. Oh, I think it. Of course, it should have been done by now, but let me see. Is it refresh? Oh, no, it was still running. So in this case, it detected a lot of pictures. Oh, did I change the? So notice these are all the faces that it detected, and you can see that has the probability that it is a face. So this is a detection model, and it has the bounding boxes for those. And if I open that image, now you can see that it detected some faces, and some others said, well, no, this is probably not a face. Notice that most of the people that are looking down, it had a hard time figuring out that there were faces. But there are, a few that were, if it could, even this person that had, I don't know if he thinks that the finger is something else in there, but it basically try to find the key points between the corners of the mouth, the nose, and the 2 eyes. And then from that picture, it found the most prominent face. So this is the face that basically was the one that it could capture and said, it uses like a centroid algorithm. So it basically said, oh, this is the biggest one that I have in the better focus, and the highest level of prediction was the one that it caught up in there. So I don't know, if that person here, get a trip to Disneyland. Oh, no, not here, too bad. All right, so now, let me go back to the slides quickly here. So again, you can see that with vectors, you can basically do this, this magic of basically finding out if vectors are in the vicinity of each other, if they're in the same direction. For example, you will have concepts that are related in different vector spaces. Like, for example, in this one, remember we did the male, female. Here is the verb tense, so walking and walked are aligned the same way that swimming and swam would be. And then, for example, countries and capitals in certain models will be lined up too. So you would have the country and the capital for different countries at about the same distance in the same orientation in that vector space. Again, remember, this is a flattened version of that. Those vector spaces would have sometimes thousands of dimensions. So obviously not easy to visualize. All right, so now I want to show you quickly, I want to show you this one before. This is from the actual data that we had in there. So you can see that woman and man and queen and king are kind of in the same general direction, but they're separated by some distance. So this is kind of what you're going to find out when you basically do component decomposition on those vectors. So okay, now let me, these are some of the ways that you can do vector comparison. So Euclidean, Manhattan, Minkowski, Chebyshev, which I think is Chase, but cosine similarity, which is the most common used one. And then for words, you can do simple things like Hamming or Liebenstein distance and things like that. All right, so now let me talk about Redis OM Spring. So this is a Spring conference, we should probably get there. So Redis OM Spring, it's an extension of Spring Data Redis, and I'll show you a couple of the things that it can do. So given a Java entity or a Spring entity, you can annotate it with Redis hash. This is straight out of Spring Data Redis. And then it will be persisted to Redis as a Redis hash. You will have your same Spring Data repository. So you can, for example, do a CRUD repository and get all the freebie methods, count, delete all, etc. Save all. I have one of my few contributors to the project here that sped up our save all method by several orders of magnitude. So we have also the ability to mark something as an ID. So basically it becomes the key, or it becomes part of the key in Redis. And now with Redis OM Spring, you have the index annotation, which allows you to basically index a field so you can search over it. And by default, it discerns the type of schema search field from the data type of the field. So in this case, a string would be indexed as a tag field, which means that you can search by specific value, not by a sounds like or starts with or something like that. There's also, you can see here, find by first name. I pass the name, and that will work just fine with Redis. But you can also do more complex things. For example, you can use the searchable annotation, which gives you completely full text search over that field. So if that name, you can use a SoundX algorithm to say, find the names that sound like that name, find the names that start with this, or end with this prefix. So you can do a lot of really complex searches. I mentioned the probabilistic data structure, so that's for a different presentation. And we have the typical things that you expect from a Spring Data project, like audit annotations, created at, who changed the entity, all those things are in there. So you can do more complex searches like find by name starting with, or find by first name, or exist by email. So again, a lot of searching capabilities. So now you also can map entities to JSON. So by mapping objects to JSON, you can do now much more complex object structures in your applications. All right, so now I'm gonna jump a little bit in here, and I'm gonna jump straight to the vector similarity. So find the right model, create your embeddings, and then store those in Redis, annotate the object that represents the field with those embeddings with a magic annotation that I created. And now you can basically use Java to search over those vectors. So I'm gonna show you the demo, which is I call it the celebrity match demo. So let me go ahead and stop this Jupyter notebook because I need a different Redis running, or a different instance. So I have my ROMs VSS celebs. So I'm gonna start that Redis container. Let me show you in Redis Insight. Let's see if it started already, yeah. Okay. So Redis, even in Docker, it starts super fast. So these are the objects that I have stored in there, and let me make that a little bigger. So notice that I have something called celebrity. Each one has an ID. There's a popularity rating for that celebrity that came out of a database, an ID, the name of the celebrity. There's a class path to a local image that basically tells you, shows you the image of that person. And there is a class object that basically is used by the framework to know what class this object maps to. And now here, obviously we don't have a visualization for this because this is a byte array that was created by the framework from that image using a defaulted image classification model. You can basically plug in your own models or change the defaults, but I picked models that are basically good enough for the average use case. So now let me run the application. This would be, I'm obviously a horrible time manager, but that's a conversation we can have over beers. So I'm gonna start the application. This application, let me show you what it looks like. So our celebrity entity, it's a Redis hash annotated entity, has ID. I can search by name because it's indexed. I can search by the popularity ranking. But here's where the magic happens. This field, it's the image, or the link to the image. As long as it's a Spring resource that can be resolved, it will find the image and then vectorize it and put it in the destination field. The destination field, you can see it's down below, which is just a by array called image embedding. And that has some configuration because you want to figure out which similarity algorithm to use. You can even put the specific model you want to use if there's multiple models loaded, and you want to figure out the dimensions of the embedding that you want. So I went with 512 in here, which metric to use to calculate the distance. So all those things you still have to kind of know and research, but the hard part of this, it's done for you in 2 annotations. Typically, you would basically end up writing a Python notebook or Jupyter notebook to do all this stuff, dump it somewhere in CSV files, and then read those into your Java objects. No, this is all Spring. On the onsave of the object, it will get vectorized too. And I'm adding the feature that if the image changes, then I'll revectorize it. It's not there yet, but it'll be there soon. And now let me show you the actual search. So in this controller, I did it all in the controller because I didn't want to add an extra service in there. But there's 2 searches. One by the, this is the celebrity. So yeah, I load the image. I did the detection that I showed you before. If there's multiple faces, I grab the most prevalent face. I crop it, I turn it into a new image, and then I vectorize it, and then I use a search command, which is right here. So the search, it's really all in here. There's some metrics in there. But again, all I'm doing in here is saying use something called the entity stream, which is kind of like a fluid API to do searching, and filter by the image embedding, use k nearest neighbors to basically match the celebrities in the neighborhood of where the embedding of your face that you submitted lands. And then I also want to embed the score of the embedding in the result. I'm going to limit it to k number of faces so I don't get a gazillion matches back. I'm going to convert that to a list. And this is an HTMX application, so there's just 2 HTML templates. And that's really it. So now let me show you what the app looks like. So yeah, dismiss that. Localhost 8080. So again, I was gonna do a webcam thing, but I couldn't get that to work. So here, let me find a file here. And here's a Spanish actor, Enrique. If you've seen, what's that series on Netflix? It was really good. The one where it's the elaborate bank heist. Well, that one. So I'm gonna upload that face. And then you can see that it matched Enrique Arce immediately. And then there's, funny, this guy was in the same series with him, Pedro Alonso. But you can see there's other faces in there. Now let me, here is Sweep the Leg Johnny. Cobra Kai? He's one of the most underrated actors, and I always thought that I didn't like Ralph Macchio in The Karate Kid. I kind of liked him, but so William Zabka. Noticed that it was a pretty good match, but the matches again depends on the model that you pick to do the vectorization. So, but you can see how fast it is. This is basically searching over this data set. I think it's 9,000 images, or 6,000 images, and the time that it's actually taking the longest is doing the vectorization of the input image. The search, actually, it's super fast. And on my soon-to-be-dying Mac, So imagine this on a production environment. You can basically find similar images immediately. Moreover, you can actually do hybrid searches, where you can basically use structured data and unstructured data to say, find images like this image, but that are wearing a red shirt. In the background, it's a park in New York City. So you could do things like that. So really, the quality of your search experiences are just limited to your imagination in how much pre-processing you can afford to do when the user gives you something. How are we doing on time?
I think you're over.
Okay, of course. So let me quickly jump to the, I did that same thing with this image, which is the largest selfie apparently. And it still took less than 2 seconds to actually find all the matches. So again, the recipe to do this in your applications would be on the slides. And I also did another one where you don't have to vectorize the input images because they're clicking on things that are already in your catalog. So you will say, find something similar to this, the typical Amazon similarity type of search. So in cases like that, if you constrain the input from the user to something that you already have vectorized and you can find by ID, then things will be way faster. So again, tools and techniques to unlock unstructured data value and get semantics out of that data are there. They have evolved greatly with all the AI models in the last 10 years. I don't feel that as developers we're going to go the way of the dodo, but we really have to get better and use these tools to actually improve how we do things. Databases like Redis in frameworks like Redis OM Spring basically can help you get this without having to become a AI or machine learning engineer. So I'm trying to put the tools out there so we can get work done without having to completely go into a new field overnight. So there's some slides in there, some links, and I will post this on my Twitter. I'll let you guys take a picture. And I do apologize for the technical difficulties early on. We have a Redis developer site, and we have Redis University. So if you want to learn more about Redis, we basically publish courses in there that are all free. You can get certifications and things like that. So that's what I have. Thank you. I know we're late. Questions?
In your example, the string was just a string. It was a mapping of the image.
Yeah, it was basically a URL, in my case, to the resources directory. So it had the class path : /, and then I used, my convention is that I'm going to use the Spring resource resolver to find resources. And that class is pretty amazing. It'll find things anywhere, given the specific type of URL. Yes?
Completely clear to me where the similarity search done in the Redis itself? Or?
In Redis, yes. So the Redis search engine that I mentioned before, when I annotate the field with the indexed, but I add the vector information, it will say I'm going to index this field as a vector. And now when I send a search command, it'll basically do everything in the back end. So it will never have to pull one of those gigantic vectors back to the network. So it all happens on the Redis side. Yeah.
You said the vector search was fast, but
Yeah.
how fast?
Well, I mean, in the vein of Redis, it's again, it really depends on the search space. And you can fine-tune it with different algorithms based on your needs. But in general, it's been faster than the competition, which is what matters. Yeah, it's pretty fast. Yeah, and remember, if it's not fast enough, you can use caching. I do know of a company that can help you with that too. Any other questions? All right, go build some demos and impress somebody.